In this video we look at a difference amplifier. Sometimes this type of op-amp circuit is called a differential amplifier. What this op-amp circuit has the ability to do is amplify the difference of two input voltages. So we'll see when we're done with our analysis that Vout will be an expression that will be able to amplify the difference between these two input voltages, V1 and V2. So I'm going to write an equation here at node A using node voltage method. So I1 in terms of voltage would just be V1 minus VA over R1, and that would just equal VA minus V0 over R2. Okay, now also because of this virtual short, again, virtual short for an ideal op-amp is when the current and voltage are both equal to 0 at the inputs. So the voltage equaling 0 means that VA, the voltage at this node, is just equal to the voltage VB, the voltage at this node, right? Because node A is attached to the inverting input of the op-amp, and node B is attached to the non-inverting input of the op-amp, and those two voltages are the same. So I can write here that VA is equal to VB. Okay, and that's since VI, the voltage across the input, or inputs, are 0. Okay, now here for node B, the expression I'm going to write here, since the current is 0 at the non-inverting input, that means all this current from V2 just travels through R3 and R4, so we have a series connection. So VB is just equal to the resistance across this resistor R4. So I can write that VB is just equal to V2, and this is just using voltage divider equation, so V2 times R4 over R3 plus R4. Alright, so what I'm going to do now is refer you to a PDF file that's on Polylearn that's under this this lecture with this video. So refer to PDF on Polylearn. That will show you the couple of steps that you need to do to get to the following expression. Okay, basically where this expression comes from is if you just take VB here and plug in for VA, since VA is equal to VB, if I just take this expression for VB and plug it into this expression for VA and then just do some algebra, I can show that Vout is equal to what you see at the very top of the page here. And what's useful about showing Vout in this form is that it shows that for a difference amplifier, Vout is just the sum of our inverting amplifier expression and a modified non-inverting amplifier expression. So here is the superposition circuit. Okay, see, both of these are superposition circuits. This one's for V1, where we leave V1 in and we get rid of V2, and then this is the superposition circuit for V2 where we get rid of V1. So if you look here, when we get rid of V2 and we replace it with the short, we'll now attach this non-inverting input, or just resistors that go to ground. So there isn't any current flowing through these resistors, right? Because there's no source in this part of the circuit. And when you have 0 current through a resistor, voltage is the same on both sides, since the voltage across the resistor is 0. So you just have ground right here on the non-inverting input. And if you have ground on the non-inverting input with two resistors connected to the inverting input, like you see here, that's an inverting amplifier. So Vout here is just going to be minus R2 over R1 times V1. Okay, and that's what you see right here. So one component of Vout for the difference amplifier comes from an inverting amplifier expression. And then if you look at the superposition circuit for V2 with V1 shorted out and grounded, well, now you have a non-inverting amplifier where at the non-inverting input you have a modified V2. It's been voltage divided. So you see your input to the non-inverting amplifier is just V2 times R4 over R3 plus R4. So this is the voltage that's being amplified by the non-inverter. So that's what you see, this term here this is the modified input voltage, and then here's our non-inverting amplifier expression, the 1 plus the ratio of the two resistors that we have seen before. So it's just this representation of V out for the difference amplifier shows that it's equivalent to a superposition analysis, where one superposition analysis gives you a non-inverting amplifier, the other one gives you this is the inverting amplifier, and the other superposition analysis gives you the non-inverting amplifier. Slightly modified, like I said, because this voltage at the non-inverting input's been voltage divided. Now, I'll refer you to the handout again. Okay, so refer to PDF. Okay, that goes with this lecture on PolyLearn for a second time, and it shows you a couple of additional steps where you can get V out to look like this expression here. Okay, so there's just some additional algebra steps between V out on the previous page and this one here. And the reason why this particular version of V out for the difference amplifier is convenient is because now if you set these two ratios equal, if you take the ratio of R2 over R1 and you set it to the ratio of R3 over R4, so these become equal here. Well, this ratio is all going to go away. It's going to equal 1, and what you're left with, okay, when you make this happen, what you're left with is that you get V out equal to feedback resistor R2 over input resistance R1 times the difference of the two input voltages, V2 minus V1. Okay, so this is why the circuit's called a difference amplifier, because as long as you make this condition of these two ratios equal, you're going to get V out equal to the difference of the two input voltages times this ratio R2 over R1, and as long as you make this ratio greater than 1, you can now amplify the difference of those two voltages. Okay, so that's where the name difference amplifier or differential amplifier, it's called either, okay, but it means the same thing, that you can amplify the difference of the two input voltages. Now, one last thing before we end the video, and that's if in addition to above, the condition above, alright, you set R1 equal to R2, right, so this ratio is 1, well now of course V out is just going to be the difference of the two input voltages, right? It's just that you're going to subtract V1 from V2, and if you do this, then we just call it a subtractor. Okay, so in the next video we'll see a application of a difference amplifier in an EKG machine, and then the last video on op amps will be something called an instrumentation amplifier.